Hello, hi Year 11. So last one for the week then. So today we're looking at a required practical linked to elasticity. So it's going back to yesterday's lesson and learning how we investigate the limit of proportionality for a spring. So that point where the spring no longer behaves elastically, when it won't go back to its original length and actually it's just stretched beyond that original length. Let's start then today with our kit quiz. So 1 to 5 on your mini whiteboards. I need to think of another way of introducing this, but we know what we're doing. This is the same every lesson. So 1 to 5 on those mini whiteboards. And then you need to match up the key terms with the definitions. So you can pause your video. Okay, so 3 minutes later then, magical. Let's go through the answers. So number 1, how easily a liquid flows. That's viscosity. So that links back to the organic chemistry topic, and it's one of the properties of hydrocarbons. And remember, something that is more viscous, like treacle, does not flow easily. So your longer hydrocarbons, they're more viscous, and that's not a good thing, which is why it's our shorter hydrocarbons that are more in demand, because they're less viscous and they flow more easily, like water instead of treacle. So thermal decomposition of long alkanes into shorter alkanes and alkenes, that's a process called cracking. So you would either use steam cracking or catalytic cracking. So a catalyst like aluminium oxide or porcelain to break down that long hydrocarbon into much, much shorter hydrocarbons because they're more useful. They ignite more easily, they flow more easily. These are the good things about them. Number 3, the distance a car travels while the driver reacts. So this is the thinking distance. So this can be affected by caffeine, the amount of sleep someone's had, whether they're driving under the influence, which obviously they shouldn't be. So all of these things can affect your thinking distance, or just maybe even the fact that you could be driving and you're a bit distracted. There could be a child crying in the back of the car. Trust me, that happens. Or it could be that you're distracted by a conversation you're having with a passenger. So all of these things can affect the thinking distance. Number 4, the distance a car travels once the brakes have been applied to stop the car. That's the braking distance. And number 5, the sum of thinking distance and braking distance. That is your stopping distance. So you're combining the thinking distance based on the driver's reactions, and the road conditions can affect the braking distance. And you combine the two to make the stopping distance. So today, again, it always makes us quite sad that we're not in the lab doing these things with you. So this is what we would be doing. We would be investigating the relationship between force and extension for a spring. So how much does a spring extend when you apply that force? We're going to look at a couple of equations today. So the first one then, to recall and apply the equation, force equals spring constant times extension. Now, we don't actually know, based on what we know about the exams in the summer yet, that you will have to remember these equations. It may be that you are given the equations and then you just need to apply them. And as we know more information, we'll let you know. But let's just say at the moment we don't know, and therefore we're going with, we need to be able to remember them and apply them. If that changes in the future, then we'll tell you, but we will definitely then have to apply them. And the second equation then is elastic potential energy. So when you stretch that spring, obviously it's got stored energy in that stretched spring, and if you let it go, that energy is going to transfer into, say, kinetic energy or another type of energy, and you work that out by doing 0.5 times the spring constant. So the spring constant is the stiffness of a spring or a material, and then you times that by the extension squared. And at this point, it would be important to mention BIDMAS. So with this equation, you should do the work in the brackets first, the B in brackets. Okay, calculate relevant values of stored energy and energy transfers, and then describe the difference between a linear and non-linear relationship. So we started to look at this yesterday when that diagonal part of the graph showed that linear relationship. So there was a direct proportional relationship between force and extension. If you increase one, the other increases. But with non-linear relationships, that doesn't happen. They're inversely proportional or indirectly proportional. So if you increase one, the other doesn't necessarily increase. Okay, So here is a practical, and this is what we would be doing in the lab. So you have a stand, sometimes called a retort stand, and you can see then that a spring is hung onto the clamp, and then there's a ruler next to the equipment, and then the weights are being added, and you would add them one at a time to slowly increase the force being applied to the spring. The ruler there is there to measure the extension in the spring. So you would have to measure the spring at the beginning with nothing on it to know its original length, and then you'd add the first weight and you'd see how much the spring has stretched, and you'd write that down. Then you add the second one and again see how much has it stretched and write that down, and then you would collect that data until you've done a suitable range of measurements. So normally 5 measurements would be what we call the minimum. So you could do 1 Newton, 2 Newtons, up to 5, and that would be enough. Now, every time you apply the weight, there will be some bouncing on the spring. So we call those oscillations. So that is something you need to be aware of. And so one of the points of this practical is that when you add the weight onto the spring, you have to wait for it to stop bouncing before you take a measurement. Okay, so here is just a model answer to go with that. So the independent variable for this practical, so that's what you're changing, is the force applied to the spring. So you're going to do this by adding the weights in 1 Newton increments. And each time you need to wait for that spring to stop oscillating. So that means we need to wait for it to stop bouncing prior to taking a measurement on the ruler. You're not going to be able to take a measurement on the ruler if it's bouncing and moving and you can't see what number it is. Okay, and then our dependent variable is always what you're measuring in an investigation. So here it's the spring extension. So how many centimeters, and then probably convert that to meters, is the spring extending by? Okay, and we would do that for at least 5 measurements. Okay. Okay, what I'm going to do is put a link to this video onto Google Classroom. So what I would like you to do now is, after I've explained this task, you just need to pause this video and then open up the link for this video, because if I play it within my recording, the sound quality just won't be very good. It's really important that you know the method for this practical. So this teacher on this video, he's going to outline it and demonstrate the method to you. He does a really good job, actually. So as he's detailing the steps involved in this practical, you need to be writing down those numbered steps. So what does he do first? What does he do second? He'll also then give you some data in a results table, and he will show that to you. So you then need to draw a results table. So I should see in your books, when you send me the picture of your work, the kind of 1, 2, 3, 4, 5, however many steps there are for the method, and then underneath a results table, and then we can talk about the results. So this is the point now, just to make it clear. You pause this video and then you go and find this link on Google Classroom, and I'll have posted it on there for you. Okay, and you can see from this picture what the teacher looks like, so you can make sure that you're watching the right video. And then once you've completed that video, come back to this one. Okay, so you've watched the video now, so thank you very much for that, and hopefully that was enjoyable. So here is the data that the teacher provided. So we've got the force, obviously starting at 0 newtons when he didn't have anything on the spring, going up in 1 Newton increments, and then the extension has been converted into meters. So we deal with our equations in meters. So he may have had to convert from centimeters to meters, I think. And then using this data, we plot a graph with a line of best fit. So this graph, weirdly, we actually switch the axes. Normally, you would put your independent variable along the bottom, which would be the force, and then your dependent variable, the one you measure, on the y-axis. But we have to do this one the wrong way around on purpose to see the right pattern in the results. So for this graph, you would do on the x-axis the extension, the y-axis you would do force. Now, if you're thinking at this moment, I don't have graph paper, I still want you to do this task. So it can still be done in your exercise book. So you can use a ruler on lined paper, and you can do your newtons, your force, just 1 centimetre apart. And then for your extension, you could do, I don't know, 2 centimetres for every increment. So I think he suggested on the video, I'm just trying to remember what he said. So I think he went up in 0.5s. And so if you follow that, then you could use 2 centimetres for every increment. Okay, so try your best then to draw a graph and we'll see what it looks like. So I'm just thinking as I'm looking at this data, I would go for my extension 0, 0.05, 0.10, 0.15, 0.20, 0.25. I'll just say that again one more time. So for this graph, for the extension, I would go up in increments of 0.05, 0.10, 0.15, 0.20, 0.25. And I probably do those 2 centimetres apart. Okay. So this is another graph that's been produced then. So same practical, the graph shows the increase in length of a spring against load, and the load is the force applied. And one of the skills you have to be able to do is called interpolation. So this is where you read data from within your data points. So it says then, use the graph to find, number 1, the load on the spring when the spring is stretched to 2 centimetres. So if you look on the y-axis, you would find 2 centimetres, and then you would use your ruler to draw a dashed line across. And you can pause the video at this point and you can actually put the ruler up to the screen, or you can just trace your pen without drawing on your own screen across to the line. So you follow it across from 2 centimetres all the way until it meets the line. And then if you track it down towards the number, and it should be quite obvious, you'll see the answer to number 1. For number 2, For number 2, the increase in length produced by a load of 2.3 newtons. So for this one, you have to find 2.3 on the x-axis, so along the bottom, follow it up, meet the line, and then take that line towards the left and find the increase in the length of the spring. And then for the last question, the length of the spring then. Now, what you don't have on this page and what I can tell you is that to answer number 3, you need a combination of number 2 and the original length of the spring. So the original length of the spring without anything loaded on it is 15 centimetres. And what you do for number 3 is you do 15 plus your answer to number 2, which would work out the total length of the spring. So pause the video now and make sure you've got the answers to 1, 2, 3. Remembering that the original length of the spring for number 3 is 15 centimetres. Okay, so the answers then we were looking for, number 1, it was 1.5 newtons. And it was quite clear if you followed it across from 2 to the line and then straight down, it went to 1.5. If you went up from 2.3 newtons to the line and then across, you ended up at 4 centimetres. And then the length of the spring when the load was 2.3 was 15 plus 4, which is a total of 19 centimetres. Okay, and that skill then is called interpolation. So time for some fluency questions now. So there's 7 questions. Some of them do relate to the diagram on the right-hand side. So what you need to do is pause the video for 7 minutes or for however long you need to take to do this task, and then we'll be ready to mark in purple pen. Okay, so 7 minutes later, Let's go through the answers. So number 1, which 2 letters on the diagram refer to the extension of the spring? It's B and C. Obviously, A and B would be the original length of the spring when there was no load. And I think you'd be looking at C to D would be where it's stretched beyond its elastic limit, so that limit of proportionality. Right, number 2, what is 100 grams equivalent to? So it was on the screen earlier. It's 1 Newton. Number 3, why do you wait for the spring to stop oscillating? So that word means bouncing before taking a reading. So it's to take a precise reading. You don't want the spring to be moving when you're trying to take that reading. Write the equation that links extension, force, and spring constant. So it is F equals KE. And that was in the learning objective. Question 5, how could you test if the spring was behaving elastically? So the spring would return to its original length when the mass was removed. If it was inelastic, it wouldn't do that. Number 6, what range of weights could be applied? So as long as you've got 5 numbers and they're all going up in even increments. So for example, instead of these numbers, you could have 2, 4, 6, 8, 10 newtons because you've got 5 numbers and they're all going up in equal increments. Question 7 then, explain what is meant by elastic deformation. So this just is in a variation of number 5. So an object has elastic deformation when an object returns to its original length after being stretched. Okay, so with all our purple pen tasks, obviously you're marking in purple, you put in ticks, and if you need to make corrections, you're adding to your notes with purple pen. Okay, so time for some work on these equations. So there's 2 equations to learn today. So F equals KE is our first equation to learn. So for a spring that is elastically deformed, the forces exerted on a spring and the extension of the spring are linked by this equation. So if we want to work out the force, we would do the spring constant times the extension. So how much is it stretched? So your force would be measured in newtons. The spring constant has a symbol of K, which is why we see F equals KE. So K stands for spring constant, and it's the stiffness of an object or the stiffness of a spring. And that's measured in newtons per meter, so N/M. And then where the extension E is measured in meters. So the extension is that stretch of the spring, and it's measured in meters. So again, you could have to convert from centimeters to meters. So just remember there's 100 centimeters in 1 meter. So you would just divide, say 20 centimeters by 100 to work it out in meters. So the spring constant is a measure of how stiff a spring is. And if the K is large, then the spring is stiff. And if it's not, then it's obviously not a stiff spring. Okay, so we're going to do some practice now. So I've put a triangle at the top so that if we have to rearrange the equation, we can. So if we're trying to work out force, we do K times E. So that's the spring constant times the extension. If we need to work out K, then you would do F divided by E. And if you need to work out E, you would do F divided by K. Remember, if you get an extension in centimeters, you need to divide it by 100 and work it out in meters. So time to have a go at these 5 questions. Pause the video and come back when you've got your 5 answers ready. Okay, so let's go through the answers. So we've got the first one, number 1, F equals K times E. So I just want you to look at the layout of my answers now. This is how you should be showing your working for all equations. So we've got the equation we need to use. Then we've got F equals 300 Newton meters times by an extension of 0.08 meters. And we have a final answer of 24 newtons. So see how the 8 centimeters in the question, you have to convert that into meters. So you just simply divide it by 100 and you get a final answer of 24. Right, second question, you need to work out K, so the spring constant. So you do force divided by the extension, which would be 10 divided by 0.025. Again, converting centimetres into metres before you do your final answer. And you get 400 Newton metres. And then number 3, you're working out F, you're working out force. You do K times E, so spring constant times extension. So from the question then 80 times by the difference in the spring, so 0.04. And then you get a final answer of 3.2. And oh my God, what have I done? I forgot to put an N after my answer. I'm very disappointed in myself. Okay, so F equals 3.2 newtons. Not good. Okay, number 4, working out K, so working out spring constant. So force divided by extension, and K equals 30 newtons divided by 0.15 meters. So again, converting from 15 centimeters to 0.15 meters. Final answer of 200. And then number 5, working out K again. And again, you have to convert 2 centimeters into meters by divided by 100, and you get a final answer of 10,000 Newton meters. So that is how you use this equation. And remembering always to put your units, unlike me for number 3. Sorry about that. Okay, so the next equation that you have to be able to use is this one. So this stands then for elastic potential energy equals 0.5 times the spring constant times the extension squared. And earlier in the lesson I mentioned BIDMAS because the bit of work you would do first is to sort out the information in brackets. So if you have the extension, then you would square that first before doing anything else. Okay. So we've got that equation at the top. So using elastic potential energy equals 0.5 times the spring constant times the extension squared. So number 1 then, let's have a go at these questions. So if you look, how do you know what bit of information is which? Well, sometimes the units helps. So with number 1, 40 Newton meters, that has to be K, that has to be the spring constant. It extends by 2.5 centimeters. So that's our extension. Obviously you need to convert the centimeters into meters first. So convert 2.5 centimeters into meters and then put that into your brackets, and then you would have to square it. And then you do the 3 numbers times by each other and you work out the elastic potential energy store. So pause the video and have a go at these 3 questions. Okay, so you can see here the answers. And it's really important every time you do an equation, you show you're working. I know we go on about this, but it is really important. The final answer, by the way, because it is referencing energy, you'd use the unit for joules, so the J. So to work out the elastic potential energy, that's the 2 E's, you do 0.5 times by K, which in the first question was 40, times by 0.025 meters squared. So you do the bit in brackets first and then you times it by the other 2 numbers, and you can see the answer there. And then you can see that it's the same for the other 2 questions. Okay. So let's have a look at some quick exam questions then. So you need your mini whiteboard. So pause the video if you need to go and get it. And let's have a look at some questions. So the first question here is actually at the bottom of the screen. Give 2 ways in which the appearance of the spring has changed. So use the before and after pictures to think about what visual clues have you got to suggest that the appearance of the spring has changed. So we're looking for 2 ways, 2 marks, 2 minutes. So pause the video for 2 minutes or take however long you need. And 2 minutes later, we're looking for any of these 2. So the length of the coils have increased. There's an increased gap between the coils. The spring has become longer or the spring has become thinner. So there are 4 options there. You only needed 2. So any of those 2, or any of those 4, sorry, would give you 2 correct answers. And that one was out of 2. Okay, so that's this week's science lessons all done. So well done. It's nearly the weekend for you guys. Don't forget to send me a picture of your work so I know how you're getting on. And have a lovely weekend.